Hi everyone, I'm John Boprowski and welcome to my webinar on a free transmit feed-forward equalizer IBIS-AMI model generator that can be used in any channel simulator. Please type any question into the chat as I proceed with this webinar. I'll have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuits and serializer, deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations or from hardware measurements. This webinar is to let you know about the process I have used for many years to generate IBIS-AMI models from any channel simulator, and it's available to you for free. What is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I learned that many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI modeling building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit simulation and measurement data, and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows or Linux machines. I'm here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I've used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create IBIS-AMI models for a transmit feed-forward equalizer. Define the FFE taps using tap values or tap codes or circuit waveforms. Include the ability to de-embed the IBIS portion from the circuit data to derive the AMI portion and generate an independent standalone IBIS-AMI model from the data. Finally, I show you how to get a copy of my free transmit feed-forward equalizer model generator for use in any channel simulator. Modeling the SerDes system in a channel simulator. Channel simulators are based on the IBIS Open Forum standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: the IBIS-AMI model. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's a transmit package, typically a channel, and a receive package. Typically, these pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. The IBIS-AMI model has an IBIS portion that has a differential input from the channel. The AMI portion typically contains a receiver continuous time equalizer, a data recovery unit, and a decision feedback equalizer. Modeling a SerDes system. A key channel simulator property to keep in mind is that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the RX AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. The key concept enables the channel simulator to achieve its fast simulation speeds. Creating IBIS-AMI models from circuit data. IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I have used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data they provided to me. In today's webinar, I provide instructions on generating transmit FFE models from circuit data. The modeling data is collected typically from a SPICE circuit simulator. Modeling other types of transmit and receive SerDes is discussed in other SerDesDesign.com webinars. To start, let's talk about the typical SerDes system test points. This figure shows typical test points for a SerDes system. For the current discussion, test points TP0 and TP1 are used for data collection. NRZ data streams are used for modeling, though the transmit IBIS-AMI models may support PAM4 as well. TP0 is the NRZ waveform. The data collected at TP1 is the transmit's SerDes differential output. The data collected includes the differential output buffer characteristics, the FFE behavioral characteristics, and differential output time domain waveforms. Here's the top-level transmit FFE IBIS-AMI model. There's an AMI input portion and an IBIS output portion. The AMI portion contains the algorithmic code that performs the equalization and does not have any impedance characteristics. The IBIS portion is for the circuit output and defines the buffer output impedance interfacing the differential SerDes channel. The model discussed here is defined as linear and time invariant. It can be used in a channel simulator statistical mode and in the time domain mode. Its characteristic is represented by its impulse response, which is convolved with the channel impulse response. There are two basic IBIS-AMI modeling options. The typical transmit IBIS buffer model is composed of an RLC circuit with additional voltage current tables for differential output pins as shown in this top figure. This IBIS buffer model is quite limiting and does not do a good job modeling the actual transmit circuit output impedance. However, for the IBIS spec 7.0 and beyond, the IBIS portion cannot be modeled using a 4-port S parameters. This approach is a full fidelity approach that will accurately represent the transmit circuit output impedance facing the differential channel. My experience has shown that most transmit SerDes designers cannot easily separate out the S4P data for the output buffer and the transmit circuit. Fortunately, the IBIS S4P data can be obtained from S2P data. I've used this approach with my customers for many years. All that is required is to measure the transmit output differential reflection coefficient. This is called the SDD11 characteristic. To be discussed in later slides, but we will also use the SDD's 11 0 Hz resistance value. To convert the S2P data into S4P data that is usable in an IBIS model, set up an S parameter schematic with this S2P file and with a 4-port transmitter as shown in this schematic below. The differential output impedance characteristic will be the same as the original S2P data. Be sure to use a linear frequency sweep with the same start, stop, and step frequencies as the S2P data. We are now ready to discuss IBIS transmit AMI modeling options. Two types of modeling approaches are provided. One approach models the transmit circuit FFE behaviorally with taps and output filter. Any number of pre and post cursor taps are allowed. The taps can be defined with scalar values or dB values. The taps can be quantized between upper and lower limits. The taps can be represented with tap codes. In all of these cases, the output filter can be represented with transmit circuit output waveforms. Another approach is to model the transmit circuit as a black box. Without a priori knowledge of the tap values or the tap filter characteristics, the transmit circuit output waveforms can be measured with the transmit circuit output loaded into a matched 0 Hz load resistance. The FFE modeling approach using taps and filter. For this modeling approach, there are various options for defining the tap states. The taps can be defined with no limits using numeric or dB values. The taps can be defined with a preset list of tap numeric or dB values. The taps can be quantized values with limits using numeric or dB values, or the taps can be defined from a table of tap codes from min, max, and step values. The transmit circuit filtering can be defined from a list of poles or from the transmit circuit output step response waveform. When a waveform is measured, it can either exclude the IBIS portion or it can include the IBIS portion. When it includes the IBIS portion, then the model automatically de-embeds the IBIS portion from the waveform to obtain the AMI portion filtering characteristic. The FFE modeling approach as a black box. For this modeling approach, the transmit circuit is characterized over a full or partial set of FFE states. The transmit circuit characterization process uses a PRBS waveform pattern that has a portion of the pattern with a consecutive set of M0s and N1s such that the M and N values are large enough to allow for state settling. The waveforms are collected into a matched 0 Hz load. This approach is typically used with one precursor and one postcursor with a defined number of drive levels. This approach requires de-embedding the IBIS circuit characteristic from each of the waveforms. This de-embedding is performed automatically during simulation for the specific symbol rate and samples per symbol used. Let's talk about de-embedding the IBIS characteristic to obtain the AMI model. In this figure, H of S is the transmit circuit input to differential output transfer function as defined by the transmit output time domain waveforms. H2 of S is the IBIS portion and is defined from the S4P data. H1 of S is the AMI portion that must be derived. Since H of S is equal to H1 of S times H2 of S, then H2 of S is the ratio of H of S divided by H1 of S. These transformations are carried out in the AMI model to obtain the equivalent time domain representation of H2 of S for use in the simulations. H1 of S for use in the simulations. Example using Keysight ADS channel sim. In this ADS schematic, the transmit AMI model is set up using the SerDesDesign.com Tx SerDes FFE with taps model. This is a behavioral model that uses transmit circuit waveform data obtained from SPICE simulations. The model will be used to generate an independent IBIS-AMI model. For this example, a SerDes channel is defined with S parameters. This plot shows the SDD21 channel characteristic. It has 23 dB loss at Nyquist, which is 13.28125 gigahertz. Thanks to Silicon Creations LLC for use of their ADS copy. Removing ADS high frequency aliasing. In this example, the S parameters go out to 67 gigahertz. the blue curve in this upper left graph, the ADS channel impulse response in the frequency domain, the red curve in the upper left graph, accurately tracks the S parameters to 30 gigahertz with some peaking between 30 and 67 gigahertz. After 67 gigahertz, the ADS channel impulse response has high frequency aliasing. SerDesDesign.com anti-aliasing, the purple curve in the lower right graph, accurately tracks the ADS response and removes aliasing beyond the S parameter maximum frequency of 67 gigahertz. This is done with no added delay as shown in the upper right graph. Modeling the example Tx IBIS. In this example, the Tx output circuit impedance was measured as S2P data. That data shows that the transmit circuit output resistance at 0 Hz is 60.82 ohms per pin. The S2P data was converted to S4P data using the approach discussed earlier. Modeling the example transmit FFE. This example is based on defining the transmit FFE with 2 precursors and 2 postcursors, each defined as dB values. PAM4 is used with 26.5625 gigabaud with 100,000 UIs used in the simulations. The Tx output filtering characteristics is obtained by collecting the transmit circuit differential output waveforms into a matched load for the FFE with cursors set to 0 dB using NRZ data. 3 corner cases are used. The waveform shown here is for the typical corner case. Modeling the example transmit FFE. During simulation, the transmit AMI model converts the Tx circuit waveform data into an equivalent filter by de-embedding the IBIS characteristic from the circuit data. The transmit AMI model automatically selects the optimal FFE configuration. The FFE configuration is used to obtain the transmit impulse response and the impulse response for the combined transmit and total channel. The model automatically de-embeds the IBIS from the waveform data. The upper plot shows the transmit model output impulse response, which includes the IBIS characteristic with all cursors set to 0 dB. The bottom right plot shows the transmit FFE response, which is an exact match to the original reference waveform data. The transmit circuit waveform data represents the cascade of the transmit IBIS portion and the transmit AMI portion. During channel simulation, the transmit IBIS model is automatically de-embedded from the transmit circuit waveform data to derive the AMI portion. When you're ready to generate the IBIS-AMI model for your configuration, set the Enable Gen IBIS-AMI to 1. That's when your simulations are as you want. And you can generate the independent standalone IBIS-AMI model by setting this parameter, along with defining the name for your generated IBIS-AMI model. The messages shown below are displayed in the Channel Simulator message panel. The IBIS-AMI models are generated. This includes the DLL file for Windows or the SO file for Linux, and these contain the encoded waveform data for all 3 corner cases. Now it's time to use the generated IBIS-AMI model. Only the parameters exported during IBIS-AMI model generation are used. The user can define the names for the exported parameters. All other states and data are encoded in the generated AMI model. The generated IBIS-AMI model can be used in any channel simulator. It contains all the relevant transmit circuit data. The hidden parameters associated with the transmit circuit are all preset and encoded in the model. Only change the user settable parameters to set the exposed FFE states. Generate as many new IBIS-AMI models as you want for free. Summary. This webinar introduced you to the free Transmit FFE IBIS-AMI model generator. It is one of the tools I've used over the past 10 years providing IBIS-AMI models to 40 plus SerDes customers. The Transmit FFE IBIS-AMI model generator enables you to define an FFE using tap values or tap codes or circuit waveforms. It supports de-embedding the IBIS portion from circuit data, and it generates portable Transmit IBIS-AMI models usable in any channel simulator. The free time-based license can be renewed for free. The tool and its generated IBIS-AMI models rely on the same time-based license. The original license is issued for 1 month. The license can be renewed for free on a monthly basis as needed. The 12-month license is also available for a fee. Removal of the license restrictions for the generated IBIS-AMI model so that the IBIS-AMI model can be delivered to anyone for use on Windows or Linux computer is available also for a fee. The Windows and Linux build project with the generated IBIS-AMI model source code, including training, is available for a fee as well. Further considerations. SerDesDesign.com has many other free IBIS-AMI model generation tools. See our store at this link. There's a Receive CTLE IBIS-AMI model generator. There's a Receive IBIS-AMI model and generator that includes a CTLE, CDR, and DFE. There's a Repeater IBIS-AMI model generator that includes back channel training. It includes the Transmit FFE generator and the receiver with CTLE, CDR, and DFE. There's also an electrical repeater IBIS-AMI model generator that includes back channel training. It includes an FFE generator and an RX FFE with CDR and DFE generator and an optical VCSEL fiber pin TIA generator. This webinar has been on the SerDesDesign.com free IBIS-AMI model generation tools. Each IBIS-AMI model generator comes with a time-based license. Use the tool for free for 1 month. Renew the free tool license as many times as you like for free. See ordering instructions for the free available tools at this link. See the link below this webinar presentation. Well, this concludes the presentation content of this webinar. I will end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@SerDesDesign.com. Thank you.